Hello YouTube, we have returned. Okay, so just a little correction from yesterday. Remember we had that trouble, or I had the trouble of defining a function yesterday? Guys, I used the with key instead. Well, the with key thing is great, but try this. Alright, so how about I go into a new document. Let's make it a calculator document. What you could do is say, I don't know, quantity. Let's say trig sine. There it goes. Of I could even do it in terms of h if I wanted. I did it in terms of x yesterday, I think, right? Let's see, all over h, and take that. No. Escape that. And take that. All right, close it. I guess I didn't really need the parentheses. I thought I had a more complicated numerator. You could store it. Now, where's the store key?
Control bar.
Control bar. There it is. I can't see the blue stuff from over here. Can you? You can see it clearer on your screen, can't you? Yeah. That's nice. That's a control var. Let's store it as, I don't know, f of, well, it's h. All right, so now if I type f, notice how it's not italicized? That means it knows what the heck you're talking about. So you could write in f of h here, and it should spit it out. Okay? You could type in, I don't know, I guess you could type in f of, if you must, I don't know, 1 plus x, and do a composition of two functions if you want. Right? You could do what we were trying to do yesterday. You could say f of, no, not that. F of 1. Where's my 1? Where it usually is. Okay, thanks. I knew that. Sine of 1 over 1, right? Can I do control enter? I can. Ooh. This is what I couldn't do yesterday.
How did you get the first step?
First step. All right, let's do it again. I'm going to do a whole new function. All right, the one we did yesterday. Okay, open parentheses, cosine. Why is it not? Can I do this? Can I do this? There you go. No! Not you. I could type it out. I mean, it's just COS, but whatever. Trig. Why isn't it moving over to cosine? Why? Trig. Move over. There it goes. Okay. Cosine. All right, so cosine of h. Close it. Minus 1. Close the numerator. Divided by h. There it is. And let's say I could do control var to store. And let's say I call that g of h. G of h.
You did control what?
Control var. Where it says the blue stuff up here is the control, and doesn't it say STO for store?
Yeah.
Enter. All right, so now I can do like I was trying to do yesterday, g of 1. But what's g of 1 going to be? It's going to be cosine of 1 minus 1 over 1. Thanks. I want the decimal version. How do I get that? Do I hit enter? Control enter. Okay, control enter will give me the decimal instead. There you go. And that's what we were trying to do yesterday. And then we could just do, this is silly, I could just type this in, but enter there and put a little decimal in front of the 1. And then control enter to get the decimal version. Right? You see what's going on? I could change it to fix 4 if I want. I'm not going to worry about that right now. And then go back up here, enter, and then go back here and throw in 100th. Control enter. Okay, and like that. Or you could use the define function. Where's the define command?
Menu.
Okay, menu, action, define. So if I define, I don't know, let's define something. Let's define something else.
Why don't you do f of g of h?
I could do that, but I'm defining a new function from scratch. So, I don't know, y of t. Let's be weird. Is equal to, I don't know, t squared minus t or something. And so if I type in y, where's my y of t, I get that. Or y of 1, or let's be risque, of 2.5. I'll get that, and so forth. All right, so you can use the store key. What happened? You can use the store key. You can use the define function.
You know if you spell out define when you spell right?
All right. So I think there's also.
Yeah, if you type define, it will define it too.
Yeah, you can use.
Well, I know you can type everything. I'm trying to use the menu. Yeah. What?
Wow.
No, but you can use this.
Well, actually, since you're on the emulator, you can use the real keyboard to type things out. See, but I can't do that because I'm pretending it's existing. By the way, don't get too comfortable, because when you get the real calculators, I want to see them every day, and you're going to be using the real calculators, not the. Okay. Are you bring them in every day? You're going to play around with the keys every day. Okay. Well, let's see. Was there another way? Oh, and there was that with key yesterday. We could use that, right? So we used the define, we used the store, we used the with. Whatever your favorite way is to plug in numbers into a function. So, okay. Yeah.
Control.
All right, we're good? We're good? Who's stuck? We're good? We're nice? Okay. All right. So here's our topic today. Does continuity imply differentiability? In other words, if a function is continuous at a point, does it have to be differentiable there? Okay. If a function is continuous at a point, it's differentiable there? All right, let me state that as a theorem. If the function is continuous at this point, it's also differentiable at this point. You can either prove it or disprove it. Can you disprove it by one counterexample? Just give me one function that makes it fail. The theorem is dead. Anybody?
Y equals absolute value.
Perfect example, right? Absolute value? Okay. So this is false because you can name one counterexample. As long as you can find one counterexample, in this case absolute value, I can't draw. Okay? Here's y, here's the origin, here's x, here's y equals abs x. Okay. Why is that bad? Why is it not differentiable everywhere? Where is it not differentiable? Why? Why is it not differentiable there? That's not the y. That's the category of undefined derivative, but that's not the y. Why is it not defined there? Because remember what the derivative is. The limit is h equals to 0 of f of x plus h minus f of x all over. It's the limit. And the limit doesn't exist unless it's the same on the left and right. But what's the derivative here? Negative 1. What's the derivative here? 1. So the limit from the right as h equals to 0 is 1. The limit from the left as h equals to 0 is negative 1. The derivative does not exist. Question, comment? Did I miss a hand? You what? I am not understanding what you're talking about. Mr. Garcia is talking in English. Would you please? All right, slowly. Yesterday we did a difference quotient thing, right? And it's a limit. It's h equals to 0, right? Now we said back last week that the limit doesn't exist unless it's the same on both sides, right? So as h approaches 0 from the right, the derivative is always positive 1. What is the absolute value of x? It's y equals x over here, and it's y equals negative x over here, right? What's the derivative of x? Chief, use the power of that. 1. You're okay with that, right? What's the derivative of negative x? Negative 1. So the derivative doesn't exist at 0. Because from the right, it's positive 1. From the left, it's negative 1. The limit doesn't exist unless it's the same on both sides. So we call that not differentiable at 0. Yeah?
Yeah, so since it doesn't exist, it's not differential, right?
Exactly. The limit does not exist, so it's not differentiable. Okay. What is the contrapositive of this conditional statement. Do you know your logic?
Geometry.
Oh God, geometry. Oh, it's Boolean logic, really. It's Boolean algebra, really.
Yeah, more or less.
What is the contrapositive of if C then D?
D then C.
Huh? D then C? No, that's the converse.
D then
Negative, not D.
C then no.
Wait, what did you say? If C
Not
then-
D, then
Yeah, that's
not C. So this is also false automatically. A statement, a conditional statement, and its contrapositive both have the same truth value. They're equivalent. So if C then D is false, not D then not C is false. So if the function is continuous at a point, it's not necessarily differentiable there. And if it's not differentiable there, it's not necessarily because it's not continuous. Notice, it's not because it's not continuous. All right. What about this? What if it's differentiable at a point? Is it automatically continuous?
Yeah.
Can you name a counterexample that makes that false?
Wait.
Well, that's hard. What's the contrapositive of that?
If not C, then D.
Not C, then not D. Can you show me an example of a function that's not continuous at a point, therefore it's not differentiable at the point?
Yeah. Piecewise?
Piecewise,
Yeah, okay. So let's see that. All right, so this is hard to show, but this is easy to show. And since they're both contrapositive, they both have to be true or they both have to be false. We got to decide, right? So you want a piecewise defined function like, I don't know, y equals,
Negative X.
oh, let's make it more fun.
2x plus 1.
Who is that?
Who is that?
Who is that? Y equals what?
X plus 1.
X plus 1, right. So for x less than 1, let's write, let's see, f of x is a piecewise defined function. It's x plus 1 when x is less than 1, right? All right, what about for greater than 1? Let's make it a jump discontinuity.
X plus 4.
X plus, actually, x
Negative
squared plus 5.
Well, negative X squared.
Negative x squared plus 5. For x is greater than or equal to 1. Not only is there a hole here, it's a jump discontinuity. So if you have a hole or a jump, it's not continuous there, therefore it's not differentiable there. So is that a true statement?
Yeah.
So what's this?
True.
Also true. So if it's differentiable at a point, it must be continuous at a point. That's the point of this lesson today. All right, so you can have a hole. Say it's just a hole. Say it's like a hole here. It's a big hole. Well, it's just one point, okay? Even if it's just a hole, not a jump discontinuity, a removable discontinuity, you can just plug in the hole, figure out what goes there, right? That's also not differentiable. Why? Because the derivative measures the slope of the tangent line there. Well, how do you draw a tangent line there? You can, but is it unique? If you draw a tangent line here, you can draw it with almost any slope you feel like. How are you going to measure any slope you feel like? That's undefined. Okay.
Did you say that?
All right. Likewise here, if you draw a tangent line here, it could look, well, that didn't line up too good.
Too low.
He's a math teacher.
How did it go into
There's your tangent line, but I could have drawn it this way. Or this way. There's no unique tangent line, so I can't measure the derivative there. The slope of the tangent line, it does not exist.
Yeah, it doesn't exist.
D and E.
D and E. That's another meaning of infinity. Not that the number is huge, not that the answer is huge, but that the answer is, there's so many different answers, I don't know what to say. Okay? So, yeah. Yeah. Likewise, at anywhere where it just like stops, right? You can draw a tangent line. No, it's not unique. Okay. So, if it's differentiable at a point, it must be continuous at that point, and if it's not continuous at that point, it's not differentiable at that point. Oh, you're so good at this. All right, so here's my question. If f of x is abs x, what's f prime? That's an x. That's an equals. Okay. Using the difference quotient, go ahead. Knock yourselves out. How do you do that? Yeah, can you do the difference quotient thing? No? F prime equals the limit as h goes to 0 of f, well, yeah, but it's absolute value, right? Okay, so absolute value of x plus h, all of that, minus the function absolute value of x all over h, right? But we were just talking about this. Isn't it different from the left and the right of 0?
Yeah.
Remember, as h goes to 0, that means delta x goes to 0. You get, right? The difference between the point where you're taking the derivative and where you're at gets closer and closer and closer and closer to the point that you're differentiating at. Okay, so this 0 is not the 0 on the graph. This 0 is your delta x is going to 0. How far from the point you're differentiating, right? So, how do you write that? Since it's different from the left and the right. Well, didn't we say on the left? On the left, it's really y equals negative x. On the right, y equals just x. Okay. So let's write that as a piecewise defined
Wait,
function.
did we say -1?
Negative x, well, the slope's going to be negative. The derivative's going to be negative. But the function is negative x. Alrighty. So use that. The limit as h approaches 0 from the left of this function, plug in x plus h. How do you subtract the negative x? You don't. You just add, right? And you got to show that that's equal to the limit from the right. And you know that it's not, but it's just going to prove it. So how do I write this difference quotient on the right side of h equals 0? Am I using the negative x or the x branch? The x branch. So simply plug in x plus h into x and you get x plus h minus x all over h. So you just got to show what you would like to see happen is that the two limits are the same, so the limit exists, the derivative exists, right? But you know already that the left side should be -1 and the right side should be, but let's just show that. How do you show that? What does this negative mean? Distributed like a -1, change the sign. So the limit as h goes to 0 from the left of negative x plus h plus x over h. Is that the same thing as the limit as h approaches 0 from the right? I don't need parentheses here really, right? Okay. Now what happens? The x is canceled. The limit as h approaches 0. What have I done? I'm so good at this, I know. Yes. I just saw it. Thank you. Who's helping me? Thank you. Yeah, distribute the negative, we said, right? You know, do as I say, not as I do. Alrighty. So the limit as h goes to 0 from the left, and what's left when you cancel the x's?
Negative h over h.
Negative h over h. But the same thing happens here. What happens when you cancel the x's? Alright, now, it's still not a plug-in limit, but negative h over h is simply -1. So, since the variable that we're taking the limit with, h, is gone, this is a constant function. This is a constant function. It doesn't matter what h is doing. It's always going to be, what is the limit? -1. And the same thing happens over here. So guess what? It's not. It's not equal. Not equal. Not equal. Good. We did it. So the limit does not exist. The derivative doesn't exist. Like we said. Right? Yeah. Good.
What's the problem they didn't mean girls?
Oh, we're going to get to that.
We're going to do
Yeah,
it?
we're going to prove that she was not a good friend.
On October 3rd?
You already told us she was right.
Huh?
You already told us she was right.
Yes, she was
because
right.
It was
Yeah.
made by
We're
like a
going
man.
to prove it. Yeah. We'll do that. All right. What about this piecewise defined function? G of x is x squared when x is less than or equal to 0, and it's 2x when x is greater than 0. That's an x. There you go. Alrighty, so what does x squared look like? Mother function. Parabola. We're only doing to the left of 0, right? So just this piece. And what does 2x look like? The line through the origin, slope 2, right? So it's like this and that. Okay. So, let's see. Is there a hole there? No. All right. Is that a cusp? No, that's still a corner. Just like absolute value, that's a corner. A cusp is where the derivative actually goes to infinity. If it was like this, I don't know, say the line was like this, and then it went like that, like the slope of the tangent line here is vertical. The vertical tangent line has a slope that's not defined. That's a cusp. But it looks like a corner anyway, right? So it's the same idea. So tell me, does the derivative exist everywhere for this guy right here?
Yes.
Really? What?
Never mind.
Ah! What have you done?
Oh my god.
How could you? There's a corner there. How can it be? The derivative here is clearly what? 2. The derivative here is what? 2x, but if you plug in 0, 0. So the slope of the tangent line here is horizontal. The slope of the tangent line here is horizontal, the slope is 0. And the slope here is always 2, right? So the derivative is 2. Yeah, it does D and E, sorry. So G
what?
prime at 0, D and E.
Can you please re-explain that?
Explain. Let's explain. Explain what?
What you just said. You just said that
What's the
the
derivative here?
is 2.
2, right? Now remember, that's the slope of the tangent lines here. And everywhere, even at 0, right? It's going to be 2. But what's the derivative of x squared?
2x.
2x. But if you plug in 0, what do you get? Into 2x. You get 0. So the tangent line slopes are getting closer and closer and closer to being 0. In other words, the tangent line here from the left is horizontal. But the tangent line here isn't horizontal.
Oh, because you're saying the derivatives of each don't match.
They don't match, right. Right. Remember, again, the derivative is a limit. So it has to be the same from the left and from the right at every point. Here, everything's nice. Here, everything's nice. But here, corner, bad. Here, cusp, bad. Who is this? I think I could say this is h of x is, I don't know, negative x when x is less than 0, and the cube root of x when x is not. That's this guy. So this is y equals g of x. This is y equals h of x. Label everything. Okay, there you go. Okay, so both of those are bad. This is called a corner, and this is called a cusp, but the idea is that the slope on the left and the slope on the right are the same, so the derivative does not exist there. Alrighty. What about... Is this a true statement?
Yes.
When you square root a square, you get an absolute value.
Yeah.
Right? Be careful. So whenever you see that, think this. A lot of times you're simplifying something algebraically, and this is going to throw you for a loop, but if you realize that it's this, things cancel and it's nice. Look, what if you plug in -5? What's -5 squared? 25. What's the principal root of 25? 5, the absolute value of -5. What if we plug in positive 4? Positive 4 squared is 16. Principal root of 16 is 4. We're really sort of being silly because I'm getting positive 4. It's really not. It's signless, but the convention is to graph it as a positive number. All right, so what if I wanted the derivative of that?
Which one?
What's the derivative of that? Let's see.
The derivative of what?
Of this.
That's
What's
not,
f prime?
Wait, you can take
But
a
that's-
derivative
We
of
just
like
did
a...
that.
that's
Yeah,
not an
equation.
equation. That's like a double equation.
Well, you could do it this way. We did it this way and it failed, right? Let's do it this way and see what you get.
Oh, you're saying that. So
Okay.
radical.
So, let's use the difference quotient definition of the derivative. What do you write?
Isn't it 1 because they're going to cancel?
know not. What do you do? What? What's the definition of derivative?
Approaches 0.
Limit as h approaches 0 of what difference in this quotient? The square root of x plus h all squared minus square root of x squared. Okay, all over h. All right, how do you simplify this then?
Very careful.
This is like...
I'm sorry, what becomes x?
Oh, the last part, yeah.
You just do that.
That part? What?
X minus H, yeah.
What x?
It's f of x plus h minus f of x over h, right? You wanted a minus here? It's plus here. You okay?
Can't
Yeah.
you?
You all right? What?
Multiply the top and the bottom by this.
Rationalize, right. The problem here is I don't know what to do with these radicals, right?
Yeah.
But you ever hear of rationalizing the denominator of a fraction? If you get stuff like the sine of pi over 4 is 1 over rad 2, that's true. But for some reason we can't divide by rad 2, it's just illegal. Multiply top and bottom by rad 2, and you get rad 2 over 2, right? The sine of pi over 4, right?
But they're not in the.
Well, how do you rationalize the numerator? This numerator.
Oh,
Use the conjugate, right? Okay. So,
You know this.
by the way,
You know this.
there's a whole story behind this. Why can't we divide by rad 2? We can't. We got computers and calculators and technology.
Do anything.
Infinite cosmic power! We can divide by rad 2. But the ancient Greeks had a problem with rad 2. Remember Pythagoras?
Yeah.
Pythagoras was not such a nice guy like you think. Pythagoras ran a cult. In this cult, they talked about 3, 4, 5, 5, 12, 13, 6, 8, 10. You can't have 1, 1, rad 2. You can't have 1, rad 2, rad 3.
What?
You can't have 1/2, rad 2 over 2, rad 3 over 2. You just can't do that.
Why?
Pythagoras' girlfriend came to one of the meetings one day and said, but wait, what if you have a right triangle, right? And both legs are equal. Well, it's like 1 and 1. What do you get? And they stoned her to death. You can't- Not only can you not divide by rad 2, because it's just, you can't write down the problem. How do you write down rad 2 in long division?
Very careful.
Very long. You can't even talk about rad 2. All right, so that's the whole problem. Anyway, so how do you rationalize this? Well, multiply the top and the bottom by the conjugate of the top. So rad x plus h squared minus, no, it's minus already, plus that. And remember in PAG, what, 3? Did they teach you how to multiply by 1?
Yeah.
What happens when you multiply by 1?
You get the same thing.
You get the same thing, right? They did that then for this.
Yeah.
What do I have to do? What didn't I do?
Put the same thing.
Got to multiply top and bottom by the same thing because I'm just multiplying by
Uno.
1. Yeah, that's all.
Do that. By
Okay.
which-
But what's nice about when you multiply conjugates, you get
The
Our rational one.
you get
X a squared minus b squared.
The first
The
like
first
two
term
terms
squared
cancel
minus the
out.
second term
you get a difference of 2 squares, right? So what happens is the radicals go away.
here.
All right. Let's show that by foiling it out, just to make sure everyone's on the same page here. All right, so limit as h goes to 0. All right, let's do a FOIL. First times first.
X plus a squared.
X plus h squared. Technically the opposite value of that, but it's right. When you square, well, I'm not going to get there. Okay, first times first. Outer times outer. Okay, so it's going to be rad x squared times rad x plus h squared. Inner times inner.
What?
same thing.
Well, this time I just wrote it backwards. Inner times inner. Negative, the same thing, right? So what happens?
Cancel.
They're going to cancel. So those are the only radicals that are going to be left. And last times last,
X squared.
negative x squared. So all the radical stuff cancels. All over h. Okay. So that's the limit. That I'm just doing what Eduardo said.
You skip the whole.
No, nothing. You don't understand. This is the secret to my success. I just do whatever he says. Secret to my success. Oh, okay. So h times that stuff. Oh, yeah. Multiply the numerator times the numerator. Multiply the denominator times the
Is
denominator.
that going to help?
Actually, it looks worse, but it's not. So, it is helpful. Hang on. So, what cancels in the numerator? You said this stuff, right? So you get the limit as h goes to 0 of x plus h squared minus x squared all over stuff.
Hey, we've been here before.
Have we been here before? To infinity and beyond. We'll go beyond that, don't worry. All right, so what are you going to do next? What do you think?
You done? You done?
Foil. That again. Foil again.
What?
Or binomial expansion. Well, in other words, what's x plus h squared? Okay, so you get x squared plus 2xh plus h squared minus x squared all over h times stuff. Okay, so now what happens? The x squareds cancel, the h's cancel, do the limit, see what you get. You should get, in other words, make sure that you can get from here to here. It's almost done. Cancel the x squareds, cancel the h's, take the limit at 0, you should get this. All right, you too. Thanks for coming. Have a nice day.